Okay, we're going to cover two sections in this video, the shapes of atomic orbitals, and we'll also be covering a fourth quantum number. So let's go ahead and get going here. So the shapes of atomic orbitals. We want to describe the shapes of atomic orbitals. So for the shapes of atomic orbitals, we're going to take a look at the third shell. So for the third shell, the principal quantum number is 3, so that's the shell. And the different L's possible are 0, 1, and 2. So these are subshells. And here, for m sub L, if L is equal to 0 and n is equal to 3, you have m sub L is equal to 0. If L is equal to 1, m sub L is negative 1. And if m sub L is, or if L is 2, m sub L can be negative 1, or negative 2, negative 1, 0, positive 1, and positive 2. So if we look at all the possible combinations, you could have a 3, 0, 0, 3, 0, 0. You could have a 3, 1, negative 1, 3, 1, negative 1, a 3, 1, 0, 3, 1, 0, 3, 1, positive 1, 3, 1, positive 1, a 3, 2, negative 2, and you can see how I can progress here. Now, this is n, this is L, and this is m sub L. And n is the shell, L is the subshell, but for m sub L, it turns out that L also gives the orbital type. So if we look at this very first quantum number, 300, the 3 tells you that it's in the third shell. The 0 tells you that it's an S subshell. And with the S subshell, what kind of orbitals are in an S subshell? And the answer is S orbitals. Now, if I cover that one up and I cover up these other ones that are 2s, if I cover those up, we have 3 possible combinations or 3 orbitals with the designation L equal 1. So because they're 1s, they're p orbitals, or they're p subshells. So this 3, 1 is a p subshell. This 3, 1 is a p subshell. This 3, 1 is a p subshell. The same p subshell. But that p subshell has 3 different orbitals. Now, what type of orbitals do you find in a p subshell? The answer is p orbitals. So you find an s orbital in an s subshell. You find a p orbital in a p subshell. And notice an s subshell has only 1 orbital. A p subshell has 3 orbitals, 1, 3. So what do you think is going to happen when that L changes into a 2? So let's take a look here. When L is equal to 2, so this is a, let's see, 0 is S, 1 is P, 2 is D. So this is a 3D subshell. This 3, 2 is a 3D subshell. How many orbitals do you find in a 3D subshell and what type? Well, a 3D subshell has 3D orbitals. How many of them do we have? 1, 2, 3, 4, 5. So you can see the progression. 1 orbital in an S subshell, 3 orbitals in a P subshell, 5 in a D subshell, 1, 3, 5. How many do you expect in an F subshell? 7. Okay, so let's take a look again at what's going on. So this is another look. And you'll notice over here, I have the little list 0, 1, 2, 3. The subshell type is SPDF, but now I've also put that the type of orbital is SPDF. Okay, so here we're looking at the earlier shells. So when you have the first shell, L can be 0. M sub L has to be 0. This is your only set of quantum numbers possible, one orbital. So what's interesting about this is if you take a look, this is a 1s subshell with one orbital. This is a 3s subshell with one orbital. How many orbitals do you find in an S subshell, whether it's a 1 or a 3? 1. Same thing if you have the second shell. The second shell, how many 2s orbitals? 1. How many 2p orbitals? 3. So that's something you kind of want to put into the bank is the number of orbitals you'll find in a particular subshell. An S subshell, 1 orbital. A P subshell, 3. A D subshell, 5. An F subshell, 7. Okay, the shapes of atomic orbitals. Let's take a look at these. So this is the shape of a 3s orbital. It looks like a sphere. You see this little thing here that looks kind of like a window in my sphere? That's supposed to be the reflection of light off of my spherical balloon. So it looks kind of like a little circle or curvy thing. I learned that from watching cartoons. Okay, what do the 3p orbitals look like? There's 3 of them. Well, one of them looks like this. Some people call this a barbell type shape. It looks like an infinity symbol. It's 3-dimensional though. And right here where I'm drawing that little dot, that's where the nucleus is. Where's the nucleus for this guy? It's in the center. So this is one of the p orbitals. This is another p orbital, and this is a p orbital. In fact, this would be called the 3px. This would be the 3py, and this would be the 3pz. So these are your 3p orbitals, and when you put them all together, you get a 3p subshell. So you can see that the 3p subshell, we don't like to draw this way because it's really confusing, okay? So, but on the other hand, when you look at these 3, you kind of think, well, they're 3 different things, 3 different atoms maybe, but they're not. These all represent 3 subshells on the same nucleus. So the 3d orbitals, there's 5 of them. Now, if you take a look at the 3p subshell, do you see how the 3p subshell roughly looks like that, kind of like a circle? Well, the 3d subshell is going to look pretty much like that, a circle. Only it's made out of this plus 4 leaf clovers. So let's take a look at why I didn't draw them. It's because I lack the skills. So here is a diagram that shows the 3p subshells, and or I should say the 3p orbitals. So here, if we look at this line across here, this is well, first of all, I guess let's look at these right here. So what I'm going to do is I'm going to do this and zoom in on that. This will only take a moment, I hope. Fancy that. If you want to zoom in on something, it helps if you try to zoom in instead of zoom out. Okay, so this is good. I'm going to hit the autofocus here. And I'm going to zoom out just a little bit. So what I want to show you here is each of these drawings, each one is one orbital. So here, this is a 1s orbital. It looks like a sphere. And this is a 2s orbital. It looks like a sphere. And this is a 3s orbital, and it looks like a sphere. Why is one sphere larger than the other? And the answer is, well, here for the 1s orbital, you're most likely to find the electron somewhere in this tiny sphere close to the nucleus. So do you remember that Bohr model where n equal 1 is close to the nucleus, n equal 2 is farther away? The same thing here. For n equal 2, you're more likely to find the electron farther away from the nucleus. And here, for the 3s, you're more likely to find it even farther away from the nucleus. Okay, so when we look at these electrons, which one is most stable? And the answer is the one closest to the nucleus because of that charge attraction that helps stabilize it. Ones that are farther from the nucleus are easier to pull away, which means they're less stable. So you'll notice that the 1s orbital looks the same no matter what the shell, just a different size. Now here we have 1, 2, 3 p orbitals in a p subshell. So these 3 orbitals, if you put them together, they look pretty much like a sphere, about the same size as that. So here you can find electrons here, here, or here. So here we got the 2px, the 2py, and the 2pz. They've labeled their axes a little bit differently than I did, but that's all right. Now, look at the 3px, the 3py, and the 3pz. What do you notice about them compared to the 2px, the 2py, and the 2pz? And the answer is hopefully that they look remarkably the same, except larger. So that means you're more likely to find a 3p electron farther away from the nucleus than a 2p electron. Now, there is no such thing as a 2D, but there is a 3D. So let's take a look at the 3D. So this is the 3D where I say it looks kind of like a bowling pin surrounded by a life preserver. So this is where you're likely to find electrons in a 3D, and they call this Z squared. What do the other 4 look like? The other 4 look like this. I call these 4-leaf clovers, but they're not flat like leaves. They're more like 4 Hershey kisses attached by the little piece of paper coming out of the aluminum foil. And so we have different orientations of those 4 Hershey kisses where they differ by their arrangement around the X, Y, and Z axes. Now, what happens if you put all 4 of these together? You put all 4 of these together, it's going to look like a sphere. Now, what do the F orbitals look like? And the answer is, that's one of your F orbitals. The other 6, I don't even want to think about. I will never ask you to draw an F orbital on an exam. I will never ask you to draw a d orbital on an exam. But I might very well ask you to draw on an exam what an s orbital looks like or what a p orbital looks like. Okay, so there we go. Some nice pictures in your book. And now you can see where my pictures come from. I need to zoom back out. Okay, so here we go. So you can see why my drawings are, they're not very good. So here's the bowling pin with a life preserver around it. Okay, so those are the shapes, and you should really memorize these 2 shapes, the sphere and the kind of a, if you will, maybe a 3-dimensional infinity sign. So let's take a look at the shapes of atomic orbitals and see how we get why it looks like a sphere or something like this. We're only going to do this with S-type orbitals because it's by far the easiest to deal with. So here we have something called a surface density plot. So this x-axis is the distance the electron is from the nucleus. So here I'm going to put a little arrow there, which means that when you go to the right, it's farther from the nucleus. And when you go to the left, it's closer to the nucleus. So this would be the nucleus. Okay. All right. Now this y-axis is the probability of finding the electron. And since my arrow is up here, we have a high probability up here and a low probability down here. So if we take a look at this 1s plot, which starts here and goes up and comes down and flattens out, This means that you're likely to find the electron somewhere in this region here where you have that big peak. What about a 2s electron? Turns out a 2s electron you can actually find here. This goes to 0 here. And then you can find a 2s electron somewhere like this distance from the nucleus. So you can see, based on the two peaks for the 2s orbital, it's more likely to be found farther from the nucleus. So this surface density plot can be turned into a radial density plot. So I have a two-dimensional radial density plot drawn here. So what I've done here is I've taken this y-axis and brought it down here. And what I'm doing here is I'm taking a look at this little peak here. And I'm saying, well, I'm going to go to somewhere around here and say, this region here is where I'm most likely to find the electron, somewhere right in there. And so that's how I draw my little circle. So this comes down to here. And since this probability also goes in the opposite direction, that's why it goes out this far over here. Now, these little dots show you that the biggest probability is finding the electron pretty close to the nucleus and less so farther away from the nucleus. So this thing looks like a disk. Now, if I were to take this disk and rotate it, it would look like a sphere, where the density plot shows that we're more likely to find the electron close to the nucleus than farther away, as you can see here. So here for the 2s, I went all the way out to here, and I said, well, that's going to be the end of my 2s. And you can see that it ends up being a pretty big circle. Now you see this little tiny hump here? So this is right here. If we follow that down, so we can find the electron here, close to the nucleus, but we can't find it right here because this goes to 0. And here, you definitely can find it in this region here. And I want to make this really dense because this is a high peak. Here in the middle, I want to make it less dense because it's a low peak. So in this particular radial density plot, you can see that we are far more likely to find the electron farther away from the nucleus than in the 1s. So this is basically calculated using Schrodinger's wave equation. So this is a psi squared, as it were, which gives us the probability of finding the electron a certain distance from the nucleus. And the last section is one more electron property called electron spin. We want to recognize that electrons also have a spin quantum number, which is called m sub s, m sub spin, which has values of plus or minus 1/2. So it turns out that when we talk about electron spin, some experimentation was done on atoms, and it was found out that based on this experimentation, that some atoms have a magnetic field. And the best way to explain the magnetic field of atoms is that the electrons spin. So do you remember before how we talked about electromagnetic radiation? There's an electric component, there's a magnetic component. Well, electrons have a negative charge. So imagine your negative charge is spinning, that's going to give rise to a magnetic field. And your electron apparently behaves, when you put it in a magnetic field, it behaves as it's spinning clockwise or it's spinning counterclockwise. And here, that's why we give the values for the spin for clockwise and counterclockwise. This one, looking from above, you can see that it's counterclockwise. M sub s is plus 1/2, and here m sub s is minus 1/2. Now, as far as clockwise and counterclockwise goes, that's really irrelevant because it depends on whether you're looking at this from the top, or if I turn it around, this is from the top, okay? So here, we give those two values, plus 1/2 and minus 1/2. They're both half because they're spinning and they give rise to the same size of magnetic field. But we give them plus 1/2 and minus 1/2 because it gives magnetic fields that are opposites. So if you had like a north pole and a south pole on this magnetic field, it would be the reverse over here. So if this were north and this is south, down here, this would be north and this would be south. Now, for these m sub s values, we also use the term spin up if it's plus 1/2 and spin down if it's minus 1/2. And the reason we use these terms is that oftentimes we designate the electron as an arrow. An arrow up means spin up, and an arrow down means spin down. What can we say about the magnetic fields of these two guys which spin up and spin down? And the answer is the two magnetic fields are in opposite directions. So here we say, since there's only apparently two types of spin, spin is also quantized. You can't have a continuous spectrum of types of spin. All right, and that is the last section. Thank you for listening. And there we go.